we cannot discuss diffusion without talking about the steady-state diffusion and non-steady-state diffusion. Let's start with one simple example. We have a copper bar and a nickel bar, then we press them together and heat up. In this example, the copper atoms will diffuse from copper into nickel, and the nickel atoms will diffuse into copper. If we are interested in the copper content or the nickel content across the diffusion couple, we'll see that the concentration is a function of time and distance. Since we have one variable that depends on the other two variables, mathematically we can describe diffusion as partial differential equations. The steady-state diffusion is actually a special case. What it tells you is that the concentration is no longer time-dependent. It only depends on the distance. You may wonder under what circumstances we can get steady-state diffusion. To achieve steady-state diffusion, you need a thin wall. In this example, it's a steel wall. Assuming it is carbon diffusing through this steel wall, on one side we have a specific concentration, on the other side we have another specific concentration. We can call that C1 on one side and C2 on the other side. For both C1 and C2, they are constants. They do not change over time. Next, we can just plot the carbon concentration across the steel wall. On the x-axis, that's the distance. On the y-axis, that's the concentration. So let's label two distance points, x1 and x2. That's the position where we have the entry plane and the position of the exit plane. Let's also label C1 and C2. The steady-state diffusion will give you a straight line. Since it is a steady-state diffusion, this profile will not change over time. To achieve steady-state diffusion, you usually need two conditions. The first is you have to have a thin wall or thin plate. The thickness of your material has to be finite. The second point is that you need constant concentrations on both sides of the plate or thin wall. If I'm interested in the carbon concentration in the middle of the plate, let's call that position x1.5, then the corresponding concentration will be C1 plus C2 divided by 2. Using this technique, you can easily find the carbon concentration in any specific point in this steel wall. To describe steady-state diffusion mathematically, we use Fick's first law. In Fick's first law, J is equal to minus D times dC over dx. J is the diffusion flux, D is the diffusion coefficient, C is the concentration, and X is the distance. In this expression, you can see there's no time involved, and this is why it's called steady-state diffusion. The diffusion coefficient D can be broken down into finite parts. D is equal to D naught exponential minus QD over RT. The D naught is the temperature independent diffusion coefficient. QD is the activation energy for diffusion. R is the ideal gas constant, and T is the absolute temperature in Kelvin. From this expression, we can tell if we increase D naught, D increases. If we increase temperature, D increases. If we decrease the activation energy for diffusion, D increases. There are some additional notes for D. The diffusion coefficient for interstitial diffusion is much greater than that for substitutional diffusion. For example, at 1000 degrees Celsius, the D for carbon diffusion in BCC iron, which is interstitial, is in the order of 10 to the power of minus 11 meters squared per second. For iron diffusion in BCC iron, which is substitutional diffusion, the D value is 10 to the power of minus 15 meters squared per second. There is a 4 order of magnitude difference. here. The second point is, if there's a small change in temperature, it will have a huge impact on the diffusion coefficient. The reason is because T, the temperature, is inside the exponential. At the end of this video, I hope you have gained a good understanding on the steady-state diffusion. In the next video, we'll look at the non-steady-state diffusion.